Hello, everybody. So today we're going to be talking about Charles's law, or the relationship between volume and temperature, or how it relates to gases. So, quick reminder about how temperature relates to molecules. Temperature we're used to measuring, right? The higher the temperature, the warmer it feels outside, the lower, the colder it is. However, what temperature is actually measuring is the kinetic energy of the molecules. And the kinetic energy is measured as a factor of two things: the mass, how heavy it is, and the speed or velocity with which it moves. So since the mass isn't changing, what's changing when you change the temperature is the speed at which the molecules are moving. So if you have a high kinetic energy, right, the molecules are moving faster than if you have a lower kinetic energy. So if you have a higher temperature, the molecules are moving faster than if you have a lower temperature. So the higher the temperature, the higher the movement speed of the particles. So Charles's law relates volume of a gas to the temperature of a gas. So as the temperature increases, right, as the molecules of the gas increase in temperature, that means that their movement is also increasing. They're moving around quicker and quicker. And as the molecules move around quicker and quicker, hitting each other and hitting the walls, they take up more space because they're moving further and further apart with more speed. So if they're taking up more space, space is measured with volume, the volume would increase. So as the temperature decreases, as the molecules move around slower and slower, they then take up less space because they are slowing down, so the volume would decrease. We have this very simple graph here showing that as temperature increases as we move to the right, the volume also increases, right? So as we move to the right, the volume, or our y-axis, goes up as well. And as we cool down, if our temperature decreases, our volume would also decrease. So since if one increases, the other also increases, we call this a directly proportional relationship. That means that if the temperature is doubled, the volume is also doubled. If the temperature is cut in half, the volume would also be cut in half. So they increase or decrease at the exact same rate. And that's useful to us when it comes to our calculations later on. So Charles's law looks like this. We have V1 for volume 1, initial volume, divided by T1, that's our initial temperature, is equal to V2, or our new volume, divided by T2, or our new temperature. And again, I mentioned this at the very beginning of the unit, but for this unit, we always have to use Kelvin as our temperature. If we have Fahrenheit or Celsius, we're going to have to convert. And to go from Celsius to Kelvin, we just add 273. So it's a pretty simple conversion, but we have to remember to do it. So I ran a couple examples for you guys, but there's also examples that you'll see in your lives. Hot air balloons, we all know about hot air balloons. How they work is implied in the name, right? They have air inside the balloon and they heat it up. They're increasing the temperature, which makes the molecules move around faster. It increases the volume of the air inside the balloon. And in increasing the volume, but not increasing the mass, it makes it less dense. And we know from, if you think way back to the beginning of the year, the less dense thing will float or rise on top of the more dense thing. So the less dense air in the hot air balloon rises above the cool air around it, which is why hot air balloons can fly. So also, if you ever have had a bag of chips or left your basketball outside during the winter, if you go out when it's really cold, you'll notice that the basketball is more deflated than it was when it was warm. This is true for anything that's sealed, right? Your bike tires, stuff like that. Whereas when it's really hot outside, it'll be a little more inflated than it was originally. And this has to do with the temperature of the gas inside that sealed container, either increasing because it got warmer or decreasing because it got cooler. So I made a couple little at-home experiments. This one shows what happens when you heat up a gas. So I boiled some water, I put a balloon in the water, and you'll see as it heats up, you'll see the balloon gets notably bigger, right? The volume inside the balloon increases. It's now filling up the entire sides of my beaker here, and it keeps getting bigger. If you did the opposite, if you had a balloon and put it in your freezer and waited a while for it to cool down, it doesn't happen as quickly, it would actually get smaller. So this is something you can try at home if you'd like, but if you heat up a balloon, it will get larger. If you cool down a balloon, it will get cooler. So that's a pretty simple one you can do at home. This next one, you can't do at home, or I would not recommend you do it at home. I'm going to explain what I did before we do the video, and that way you'll understand what happened. So here I have, it's dark, and you'll see why in a minute. I have just an empty milk gallon. What I did was I put some ethanol in it, and I shook it around to make it so the ethanol evaporated some. So there's lots of evaporated ethanol gas inside, along with oxygen and normal air. I'm going to quickly heat up the inside of the milk gallon here. And then when it's really hot, I'm going to seal it. I have a balloon that I filled with water that I just put on top, and it seals it. And then the air cools down really quickly. And because it cools down, the temperature decreases really quickly. The volume of the air also decreases really quickly. And you'll see what happens to our milk gallon here. So you can see, right, the fire heated up the gas inside really, really hot, really, really quick. As soon as I deprived it of more oxygen by sealing the top, the fire went out, and all of a sudden, the hot air wasn't being heated anymore, and it cooled down really quickly because there's a very low specific heat capacity. If you think back to our thermo unit, it's a very low specific heat. It cools down really quickly, and then because it cools down so quickly, the temperature decreases so much, the volume inside also decreases, and you can see the gallon of milk or gallon of air shrinks to be less than a gallon's worth of volume, right? And that crunches in the milk gallon here. So those are two applications of Charles's law, right? One, we are increasing the temperature and therefore increasing the volume with the balloon and the boiling water. The other one, we are decreasing the temperature and therefore decreasing that volume, as you could see with the gallon of air. So when it comes to the calculations, they're pretty straightforward, just a little bit of algebra. Here, move my face so we can see, we have a balloon, and it's initially filled with 0.88 liters of air at room temperature. So room temperature is about 23 degrees Celsius, give or take. That's going to be our room temperature for this problem. Then it's placed in the freezer for 2 hours. When we take it out of the freezer, it's not going to be at room temperature anymore because it's been in the freezer, and the volume of the balloon has gone down. It's now 0.80 liters of air inside. So the balloon got a little bit smaller, like I was mentioning earlier. So given the relationship between volume and temperature that we know, we want to be able to figure out what is the temperature of the freezer. So we use Charles's law, which is V1 over T1 equals V2 over T2, and we use Kelvin as our temperature. That's important, and I'll show you how to do that in a moment. So just like with all the other formulas like this, we just go and try and find each variable individually. So V1, to find our initial volume, we know that the balloon is filled with 0.88 liters of air. That would be our initial volume. And it says at room temperature, which is 23 degrees Celsius, that would be our T1. So you can write these down if that helps you. But V1 would be 0.88 liters. T1 would be 23 degrees Celsius. But again, and I cannot stress this enough, you need to use Kelvin as our temperature unit. So to go from 23 Celsius to Kelvin, we just add 273 to the 23 that we have. We end up with 296 Kelvin here. Next up, we need to look at the right side of our equation. Do we know what V2 is? So it says when taken out of the freezer, the balloon held 0.80 liters of air. That would be, liters as a volume unit. That would be our final volume, or our V2. T2 what is the temperature of the freezer? That's also going to be the temperature of the air that just came out of the freezer. So that is what we need to figure out. So V2 would be 0.8 liters. T2 is going to be our unknown or our variable. So then we just plug all these in to our equation here. So for V1, we would plug in 0.88 liters divided by 296 Kelvin. That's our T1 here. That is equal to our V2, which is 0.80 liters, divided by our variable of T2. And then, now you have an equation with one variable, you just use a little bit of algebra to solve it. We'll walk through that on the next slide, but it's just algebra from this point forward. So, this is the exact same thing I had previously, right? V1 over T1 equals V2 over T2. We need to solve for T2. Our variables in the denominator, so there's a couple extra little steps we have to do to fix that. First thing we have to do, or the first thing I like to do, is I like to just solve or combine all the terms on the side that doesn't have our variable. So if I take 0.88 divided by 296 Kelvin, you end up with 0.00297. That's all the terms on the left-hand side combined into one term equals 0.80 over T2. The right-hand side still has our variable in the denominator. So to fix that, we multiply both sides by T2. And if we do that, these cancel, right? So we have one on top, one on bottom. And now we have T2 times 0.00297 equals 0.80 liters. So that's what we have here, right? After the T2s cancel on the right-hand side. So now our variables in the numerator. Great. Now all we have to do is get rid of everything else on the left side of the equation. To do that, we would need to divide, since we're multiplying, we need to do the opposite and divide by 0.00297. So we do that to both sides. We end up with T2 equals 0.80 divided by 0.00297. If you plug that into your calculator, you get 269 Kelvin. So Kelvin is a temperature unit. That would be our final temperature. Fantastic. However, and this is an acceptable answer, if you plug this in or give it to me, and if I'm not asking for specific units, it's totally fine. However, the problem initially gave us degrees Celsius, so it's good just etiquette to give your answers units and the units you were provided. So if we wanted to do one extra step and convert this from 269 Kelvin to Celsius, we would just do 269 minus 273, and that would give us -4 degrees Celsius, which would be the temperature of our freezer. That makes sense, right? It's below 0 Celsius, which is the temperature that water freezes at. This is a logical answer for us to come to given the circumstances that we're working with. So that's it. You just need to look at the problem, find each variable, solve for your unknown, and remember, if we're working with temperature, which we are with these problems, you need to convert it to Kelvin before you do any of this math. If you do not convert it to Kelvin, you will get the wrong answer every time. So be careful, take your time, make sure you have the proper units, and you are good to go.